Every black hole is a bomb, not a metaphor, a literal detonation frozen in slow motion by the most extreme time dilation in the universe. Inside, the material already bounced, the rebound finished before a photon could cross an atom. But nobody sees the blast because the outside clock runs billions of years behind the inside clock. The explosion plays out in silence, stretching across eons. The oldest bombs, the ones built in the first fraction of a second, are finally going off. Every black hole that has ever formed is running the same detonation. Everyone. The universe does not allow a permanent crush. A density floor exists beneath collapse, and when matter hits that floor, the matter comes back. The question is, what happens when the first detonations finish? The signals were predicted years before anyone knew where to look. Then mysterious millisecond flashes started arriving from deep space, and one source was confirmed. But the distant flashes, the ones arriving from billions of light years away, remain unexplained. A second origin is hiding in the data. The darkest objects in the universe are not graves. The darkest objects are storage containers, and the cosmos is beginning to open them. This video is one entry in a much larger series. If you want to see where the rest goes, hit that like button and subscribe so you do not miss what comes next in this story. Black holes are the most trusted prediction in all of physics. The math is clean. The logic is airtight. A star runs out of fuel, the core collapses, and gravity wins. Nothing escapes. Nothing returns. The crushing point at the center is the last line of the story. For nearly a century, every physicist on the planet accepted that ending as fact. But the ending was never a prediction. The ending was a confession. When Einstein first published general relativity in 1915, the equations described how mass bends the shape of space and time. The equations worked beautifully for planets, for orbits, for light bending around the sun. Within months, Karl Schwarzschild, a German physicist serving on the Eastern Front during World War I, solved the equations for a perfectly spherical mass. Schwarzschild was dying. An autoimmune disease was destroying his skin, while artillery fire shook the ground outside his quarters. Between treatments, Schwarzschild worked through the calculation. The solution described how space curved around a concentrated mass, and the solution contained an alarming feature. At a certain radius, the curvature became infinite. At the center, the density climbed without limit. Every number in the calculation spiked toward a value no instrument could measure, no experiment could reach, and no mind could picture. Schwarzschild sent the solution to Einstein and died 2 months later. Einstein studied the result and dismissed the infinite density as a curiosity that nature would never produce. Nature disagreed, and the disagreement took decades to fully register because the idea of a star collapsing to infinite density struck physicists as absurd. Arthur Eddington, the most prominent astrophysicist of the era, argued publicly that some unknown force must intervene before the collapse becomes total. The collapse could not be real. Eddington was so convinced that he dismissed Subramanian Chandrasekhar, a young physicist who had demonstrated that massive stars have no escape. Chandrasekhar presented the result at a Royal Astronomical Society meeting in London in 1935. Eddington stood up immediately after the presentation and attacked the conclusion. The audience sided with Eddington, and Chandrasekhar left the field of stellar physics. Chandrasekhar was right. Eddington was wrong. And the confrontation cost the scientific community decades of progress because the mathematics of total collapse was shelved, buried by the authority of a famous voice rather than tested against the evidence. Over the following years, physicist after physicist confirmed that the Schwarzschild solution was not an artifact. Robert Oppenheimer and Harton Snyder showed in 1939 that a sufficiently massive star has no mechanism to halt the collapse. Gravity overwhelms every opposing force in the star. Electron pressure fails first, then neutron pressure collapses under the weight. Nothing remains to push back. The matter falls inward, density climbs, curvature spikes, and the equations terminate in a singularity. Physicists gave that point a name, the singularity. And the singularity sat at the center of every black hole model, like a period at the end of a sentence, clean and final and undeniable. Textbooks printed the diagram, and lectures explained the logic. Graduate students memorized the math. Roger Penrose proved in 1965 that singularities are not merely possible, but inevitable, that any star collapsing past a certain threshold must produce one. The theorem earned Penrose a Nobel Prize. Stephen Hawking extended the result to the universe as a whole. The singularity became the most confident prediction in gravitational physics, the one claim every physicist agreed upon. When enough mass concentrates in a small enough volume, the theory predicts infinite density, and the story ends. Except the theory had not spoken. What looked like a final verdict was actually the theory admitting failure. A singularity is not a place. Instead, a singularity is a point where the math produces an answer of infinity, and infinity is not a number the universe can reach. When an equation outputs infinity, that equation is not describing reality. Rather, the equation is describing the boundary of the model, the edge where assumptions collapse under pressure. Einstein himself understood this problem. As the architect of general relativity, Einstein warned colleagues that the theory would fail at extreme densities. General relativity was built for weak gravitational fields, moderate curvatures, systems where quantum effects could be safely ignored. But the center of a collapsing star is none of those conditions. At the center, quantum mechanics and general relativity, the two most successful theories in the history of physics, are forced to occupy the same point. Very small and very large collide, and neither theory survives the collision. So for a century, every black hole diagram carried a secret. That dot at the center was not a destination. That dot was a blank, a gap in understanding dressed up as an answer. Physicists knew the gap was there. Conference talks acknowledged the problem. Papers used careful language, describing the singularity as a prediction of the classical theory rather than a prediction of nature. But nobody had the tools to fill the gap. No quantum theory of gravity existed, capable of surviving the extreme conditions inside a collapsed star. Two pillars of modern physics, the theory of the very large and the theory of the very small, had been built in parallel for nearly 100 years, and at the one point where both pillars needed to support the same structure, both collapsed into each other. Put plainly, the singularity was not a conclusion. Rather, the singularity was a question mark wearing the disguise of a period. Then in 2014, two physicists stopped treating the question mark as a period and started treating the gap as an answer waiting to be replaced. Carlo Rovelli at Aix-Marseille University in southern France and Francesca Vidotto at Radboud University in the Netherlands wrote a paper, 6 pages long, shorter than most abstracts in the field. Their argument was built not on speculation, but on a result already proven in a different domain. Physicists working in loop quantum cosmology had applied quantum gravity corrections to a collapsing universe. What emerged was stunning. At the beginning of time, the Big Bang singularity, the infinite density that supposedly started reality, vanished. A bounce replaced the crushing point. Instead of emerging from nothing, the universe had contracted to a maximum density, hit a floor, and rebounded. Not a flaw imposed by hand, not an assumption. A flaw that emerged from the mathematics of loop quantum gravity, a framework where the geometry of space has a granular structure at the smallest scale, like atoms in a crystal. Compress that geometry hard enough, and the granular structure pushes back. What results is a maximum density the universe enforces, roughly 10 to the power of 93 grams per cubic centimeter, a value called the Planck density. Nothing, no matter, not radiation, not even the full weight of a collapsing cosmos can exceed that number. Abhay Ashtekar at Penn State had demonstrated the cosmological bounce in detail, no hand-waving. Precise numerical simulations from the Ashtekar group showed a stunning result. The wave function of a collapsing universe reaches Planck density and rebounds. Ongur, precise numericals, rebounds, deterministic, survived. Before and after the bounce connected with no break, no loss, no singularity. Not a single piece of quantum information was destroyed in the transition. John Wheeler, the physicist who coined the term black hole decades earlier, had predicted exactly this outcome. Wheeler wrote in 1967 that the wave packet does not and cannot follow the classical history into the singularity. Wheeler did not have the math to prove the prediction. Decades later, the Ashtekar group did. Rovelli and Vidotto took the logical next step. If the cosmological singularity bounces, why would the black hole singularity survive? Same physics, same mechanism. When matter collapses past the point where classical physics breaks down, that matter does not reach infinite density. Instead, that matter hits the same floor. Quantum pressure, the same force that prevented the universe from reaching zero volume, prevents the star from reaching infinite density. Collapse reverses and matter rebounds. No infinite crush, no endpoint, no grave. Just a bounce, and not a gentle one. A rebound at the densest possible state the universe allows, where every particle of the collapsing star compresses into a volume smaller than an atom. At that density, quantum pressure flings the material back outward, and no force in existence can overwhelm the rebound. But the timing destroys every intuition. From the perspective of the matter falling inward, the entire bounce takes less time than a photon needs to cross an atom. Material drops, compresses, hits the floor at Planck density, and rebounds. A passenger blinks. Journey over. From the perspective of an observer watching from the outside, the bounce has barely started. Gravitational time dilation, the same effect Einstein predicted more than a century ago, stretches the interior microsecond across billions of years of exterior time. Both clocks, inside and outside the black hole, are correct. Yet the two clocks disagree by a factor so enormous that the word disagreement fails to capture the scale. One clock measures a blink, another measures longer than the current age of the universe. Both describe the same event. Think of a firework launched into the sky. A fuse burns, a shell detonates, and the burst lasts a fraction of a second. Now imagine filming that burst with a camera running at 1 frame per trillion years. Real explosion. Already happened, but the footage plays so slowly that the first spark has not yet appeared on screen. Every black hole is that footage, the bounce already finished, but the replay has not. That gap between the two clocks is the engine of what follows. Every consequence, every explosion, every signal, every philosophical reversal in this story flows from the mismatch between the microsecond interior and the billion-year exterior. Inside, the bounce finishes before a heartbeat. Outside, the universe has not aged enough for the slow-motion replay to reach the final frame. Rovelli and Vidotto called the compressed core a Planck star, not because the object is the size of the Planck length, but because of the density at which the bounce occurs. Compared to the Planck scale, the Planck star is enormous. For a stellar mass black hole, the compressed core reaches roughly 10 to the power of -10 centimeters, smaller than an atom, but still more than 30 orders of magnitude larger than the Planck length. Instead, the name comes from the density. At Planck density, the maximum density the universe allows, quantum pressure reverses the collapse. No new exotic object invented by speculation, just what the math produces when quantum effects are included at the moment where the classical equations fail. And Rovelli and Vidotto did not patch the old theory. No small correction was added to the singularity. Instead, the singularity was removed entirely. That crushing point at the center of every black hole diagram, the point that a century of physics had treated as the final word, was never a feature of reality. Rather, the crushing point was the math-confessing failure, pushed beyond the domain where the math worked. When correct physics is applied, the infinite point disappears. A density floor appears. A bounce begins. 6 pages delivered this result, short enough to print on both sides of 3 sheets of paper. A century of revision arrived in a document shorter than most grant applications, and the size of the argument is part of the point. No deep truth required a deep explanation to dislodge. Instead, the singularity was a shallow error, a confusion between the limits of a model and the limits of reality. Simple correction. The universe has a maximum density, and at that density, collapse reverses. Every consequence in this story follows from those two sentences. The implications ripple outward in every direction, and none of them are small. Not a grave, not a place where matter goes to die. A black hole is a phase in the life of a star, a temporary state where the core sits at maximum compression, while the exterior clock runs so slowly that the bounce appears frozen from the outside. Permanent in appearance because no observer can wait long enough to see the conclusion. But the conclusion is already happening. The matter already bounced, and an interior passenger already blinked. Only because the universe outside has not aged enough for the slow-motion replay to reach the final frame does the rebound remain invisible. Every dark silhouette surrounded by glowing gas, every black hole ever captured in a photograph is not a permanent fixture of the cosmos. None of them are. Each of those objects is a bounce in progress, a detonation playing out so slowly that the flash has not yet reached the surface. And the viewer who looked at a black hole with fear, imagining a permanent grave, was looking at a far stranger object, a waiting room, a storage facility running on the slowest clock in the cosmos. The oldest black holes in the universe have been running the longest. And the first question that rises from all of this is the one that drives the story forward. If the bounce is real and the matter comes back, what happens when two clocks, disagreeing for billions of years, finally reach the same moment? Picture a firework. The shell detonates, the burst fills the sky, and the entire display lasts less than a second. Now imagine pressing the slow-motion button on a camera, so extreme that each frame takes 1 trillion years to advance. The explosion already happened. The burst already faded. But on the screen, the first spark has not yet appeared. Every black hole in the universe is that footage, a detonation already completed on the inside, while the outside has barely begun to register the first spark. The bounce finished billions of years ago. The replay has not even started. That gap between the two clocks is not a curiosity. That gap is the engine driving everything that follows. Inside the collapsing star, the rebound occupies a duration shorter than any clock can register. The material drops, compresses, strikes the density ceiling, and reverses direction. A passenger riding the collapse blinks once. Journey over. From the perspective of that passenger, the entire life of the black hole occupies a sliver of time so thin that no human unit of measurement can capture the duration. Darkness never arrives. Neither does any sensation of being trapped. Collapse and rebound happen in a single unbroken motion, faster than a nerve impulse traveling from fingertip to brain. Before the passenger has time to register what happened, the density surge is over, the horizon is behind, and the other side is already visible. No waiting and no suffering. Just a compression and a release, like squeezing a spring and letting go. Except the spring is a star. The compression reaches the maximum density the universe permits, and the release fires the material back outward at a velocity determined by quantum gravitational pressure. But the observer watching from the outside sees none of that. From the outside, the curvature of space-time near the collapsing mass warps the flow of time so severely that the interior microsecond stretches across billions of exterior years. The same event, two durations that cannot be reconciled, both clocks running correctly. Neither clock is broken, neither clock is an illusion. General relativity does not say that one perspective is real and the other is fake. Both are real. Both are physical. Neither measurement contradicts the other. What looks like a paradox is actually a feature of curved space-time, a direct consequence of mass bending the shape of time. Stronger gravitational fields produce greater slowing, and the exterior clock falls further behind the interior with every increment of curvature. And inside a black hole, the gravitational field is strong enough to stretch a microsecond into an interval longer than the current age of the cosmos. The same blink that felt instantaneous to the falling matter looks permanent to the rest of the universe. Einstein described the time dilation effect in 1915, and the description has survived every experimental test for more than a century. Clocks aboard GPS satellites run faster than clocks on the surface of the Earth by a measurable amount, roughly 45 microseconds per day. The global positioning system corrects for the difference every 12 hours. Without the correction, navigation signals would drift by more than 10 kilometers per day. Within a week, the system would be useless. Gravitational time dilation is not exotic physics locked inside a notebook on a university desk. Gravitational time dilation is infrastructure. Every phone in every pocket, every airplane instrument panel, every missile guidance system on the planet relies on one reality. Clocks tick at different rates depending on how deep the clock sits in a gravitational field. That correction uses the same mathematics, the very same equations that describe the two clocks inside and outside a black hole. The only difference is scale. On the surface of the Earth, the time dilation is subtle, 45 microseconds per day, invisible without atomic precision. Near a neutron star, the effect becomes obvious, clocks slowing by fractions of a second per hour. At the event horizon of a black hole, the slowing becomes total. Wheeler saw where that scaling led. The physicist who coined the phrase black hole in 1967, during a lecture at the Goddard Institute in New York, warned the field that the classical picture of infinite collapse was incomplete. Wheeler committed a single declaration to print, one that would take the rest of the century to vindicate. The quantum state of collapsing matter, Wheeler insisted, cannot track the trajectory that classical equations prescribe toward infinite curvature. The prediction was sharp. Wheeler did not say the classical picture might fail. Wheeler said the classical picture cannot succeed. That prediction arrived decades early, before anyone had built a framework capable of confirming or denying the claim. Wheeler saw the answer, but lacked the tools to prove what he saw. The tools arrived later, built by a generation of physicists Wheeler helped train. The bounce that Ashtekar later proved in cosmological models and that Rovelli and Vidotto extended to black holes now had an explicit geometry. On the 4th of July in 2014, Haggard and Rovelli published the metric that made the bounce physically concrete, a complete space-time description showing black-to-white hole tunneling, valid everywhere except the quantum transition zone. The bounce was no longer a speculation. The bounce was a solution, obeying every rule the universe imposes on space-time, except at the single point where the classical rules were never valid. But that solution carried a hidden consequence, one that nobody anticipated until 2024. Christodoulou and De Lorenzo had been calculating the geometry of space inside a black hole using standard tools from general relativity. The calculation asked a deceptively simple question. As a black hole ages, as the exterior clock ticks forward, what happens to the volume of space enclosed within the event horizon? The intuition says the answer is obvious. A black hole shrinks over time. Hawking radiation bleeds energy from the horizon and the surface area decreases. A dying black hole gets smaller. The radius contracts. The shadow dims. Every physicist in the field expected the interior to shrink alongside the exterior. Safety in that assumption came from one fact: the exterior was the only side anyone could observe, and every instrument pointed outward. Further reinforcement came from the no-hair theorem, a result stating that two black holes with the same mass, charge, and angular momentum settle on the same external geometry, identical on the outside. Two objects indistinguishable to every telescope, every gravitational wave detector, every electromagnetic survey ever conducted. That confidence convinced physicists that the exterior told the full story. Outside appearance became the signature. Outside appearance became the identity. And the interior was assumed to follow. Christodoulou ran the calculation at the University of Marseille, applying the maximal volume slicing technique to the Schwarzschild interior. De Lorenzo verified the numbers independently. Both arrived at the same result, and that result broke the intuition completely. The interior volume grows, not slowly, not in bursts, linearly, steadily, without pause. For every unit of time that passes on the exterior clock, the interior adds volume proportional to the square of the mass. A black hole with 10 solar masses gains interior volume at a rate so rapid that within a few billion years, the space inside the horizon exceeds the volume of a typical galaxy. Within tens of billions of years, the interior dwarfs anything the exterior universe contains at comparable scales. What appears to be vanishing from the outside is quietly, steadily becoming enormous on the inside. Outside, the horizon contracts. Inside, the volume balloons. Two sides of one object, moving in opposite directions, each obeying the same equations but producing conclusions that directly contradict each other. The interior stretches like a tube whose walls narrow while the length extends, and the total volume increases even as the external surface area contracts. Picture a deflating balloon, skin wrinkling and tightening, while the air pressure inside somehow climbs. A distant observer concludes the balloon is dying, but someone standing inside would see the walls pulling further apart, the interior stretching into a space larger than the original balloon ever contained. A black hole behaves like that balloon, except the numbers are beyond moderate. An old stellar mass black hole, one that has been radiating for trillions of years, possesses a horizon smaller than an atom, yet encloses an internal volume larger than many galaxies. Dying on the outside, expanding on the inside. Both descriptions coexist in the same object, separated only by a horizon, the boundary between two measurements of space that cannot agree. Every step of the calculation follows directly from the Einstein field equations, the same equations that predict the existence of black holes, the expansion of the universe, and the bending of light around massive objects. No new physics required. Not a single exotic theory needed. Zero speculative frameworks bolted onto the standard model. The mathematics was available for decades. The calculation was straightforward. A graduate student with the right background could have run the numbers in the 1980s. Nobody did. And yet the results surprised the field because physicists had been studying black holes from the outside for so long that nobody stopped to compute what was happening inside. Outside measurements were available. Outside data were accessible. And so the outside became the entire conversation. The interior, sealed behind a horizon that no signal could cross, was assumed to mirror the exterior. Shrinking outside meant shrinking inside. That assumption was wrong. A false equivalence between external appearance and internal reality had lulled the field into complacency. Nothing in the no-hair theorem says anything about the interior. Two black holes can look identical from the outside and possess vastly different internal volumes, depending on age. A young black hole that formed yesterday and an ancient black hole that formed billions of years ago, both with the same mass, appear identical to every external instrument. But the ancient one has been accumulating interior volume for billions of years. Interior volume in the old black hole dwarfs the interior of the young one by a factor beyond comprehension. Age is invisible from the outside, but written across every cubic meter of the interior. The no-hair theorem, the result that convinced a generation of physicists that the exterior tells the full story, says nothing about what hides behind the horizon. Two identical masks, two radically different interiors, and no instrument on the outside can tell the difference. Consider what that means for one specific object. Sagittarius, a star, the black hole at the center of the Milky Way, carries a mass of roughly 4 million solar masses. The exterior horizon spans about 12 million kilometers, smaller than the orbit of Mercury. But that horizon has been enclosing a growing interior for at least 10 billion years. By the time the exterior has shrunk to a point, the internal volume will have expanded to a scale that defies any visual analogy rooted in human experience. A container the size of a city on the outside, larger than a supercluster on the inside. The implication for the Planck star proposal cuts deep. If the interior volume grows over time, then an old black hole contains far more room than a young one. No cramped chamber waits at the center. Instead, the rebound occurs inside a container, one that has been stretching for the entire life of the black hole, billions of years of silent expansion. Matter that fell in at the beginning of the collapse has been riding that expansion, moving further from the horizon with every tick of the exterior clock, drifting through a geometry that grows more spacious as the exterior appears to contract. When the bounce finally completes, the material emerging from the white hole has been traveling through an interior geometry, one that no external measurement could have predicted. The waiting room is not small. The waiting room is immense, and the immensity has been growing in silence while every astronomer on the planet assumed the object was shrinking. Every shadow ringed by superheated plasma, every void in the images released by the Event Horizon Telescope collaboration represents a temporary condition masquerading as permanence. Not one of those dark regions is a final state. Matter that fell in, some of the matter billions of years ago, has already bounced. Already, the material is heading outward. Already, the passenger completed the round trip. But the exterior cosmos has not accumulated enough elapsed time for the slow-motion record to reach the concluding moment. The explosion is real. The broadcast has not finished transmitting, and nobody watching from the outside has any way to fast forward. Every black hole ever photographed is a bomb in the middle of detonating, and the detonation is so slow that the flash will not arrive for longer than the current age of the cosmos. The two-clock mismatch carries a pointed consequence for the oldest black holes in the universe. Not every black hole formed from the death of a star. In the first fraction of a second after the beginning of the universe, density fluctuations in the primordial plasma could have compressed pockets of matter past the threshold of collapse. Those compressions would have formed black holes before the first atom existed, before the first photon escaped the primordial fog, before the cosmos had cooled enough for hydrogen to form. No supernova preceded the formation. Gravity alone did the work, compressing pockets of plasma past the point of no return. The raw density of the infant cosmos was enough. Physicists call these objects primordial black holes, and the objects have been sitting in the universe since before the first star ignited. Primordial black holes were small, smaller than mountains. Some carried less mass than the asteroid belt, compressed into volumes smaller than a single proton, yet massive enough to curve space-time into a horizon. The size matters because the mass of a black hole determines how long the exterior replay takes. More massive black holes have longer replays. Less massive ones finish sooner. A stellar mass black hole, the kind formed when a massive star collapses, runs an exterior clock measured in timescales so vast that the current age of the universe, all 14 billion years of elapsed time, barely registers as a fraction of the total weight. For a 10 solar mass black hole, the exterior replay would still be running, long after every star in every galaxy has burned out. Those stellar black holes will be replaying their bounces for eons beyond counting. No civilization in the observable universe will survive long enough to witness the final frame of a stellar mass bounce. The universe could age 1 trillion years, and the slow-motion footage would still be crawling through the opening frames. But primordial black holes operate on a different schedule entirely. Rovelli and Vidotto calculated the bounce time as a function of mass. For a black hole at the solar mass scale, the exterior duration of the bounce stretches past the heat death of the cosmos. For a black hole with the mass of a mountain, the duration shrinks to billions of years. And for a black hole with a mass near the Planck scale, the number drops further still. The replay timer for those small, ancient black holes is measured not in trillions of years, but in billions. Roughly the same order of magnitude as the current age of the universe. That coincidence is not a footnote. That coincidence is the entire drama of the Planck star proposal. Almost 14 billion years have passed since the beginning. The smallest primordial black holes, the ones that formed with masses near the Planck scale, have already completed the replay. Slightly larger ones are approaching the final frame now, and a population in between, black holes that formed with masses between roughly 10 to the power of 14 grams and 10 to the power of 16 grams, sit in a narrow window. For those objects, the bounce duration falls within the age of the cosmos. Those objects are finishing the oldest detonations in the universe. The bounces that began in the first heartbeat of the cosmos might be reaching the moment of completion right now. Not in the distant future, not in an abstract calculation pinned to a whiteboard. Now, in the same era where radio telescopes scan the sky every night and gamma-ray observatories catalog every burst of energy arriving from deep space. If a primordial black hole finishes the replay, the white hole that emerges releases a burst of energy concentrated in a single flash. Energy depends on the mass of the original black hole. Wavelength depends on the size of the horizon at the moment of emergence. For black holes near the Planck mass, the predicted signal falls in the gamma-ray range. For slightly larger ones, the signal shifts toward radio frequencies. Barrow and Rovelli published that prediction in 2014, before anyone had confirmed the source of the mysterious millisecond flashes arriving from deep space. Their math came first. Observation came second. A signal was described before the signal had a confirmed source. Every parameter is calculable. Every energy budget is constrained by the mass. And the timing for primordial black holes formed in the first fraction of a second places the arrival of those signals squarely in the present epoch. But are the flashes real? Do the predicted signals match anything telescopes have actually detected? Or does the entire framework collapse the moment the calculations meet the data? Small black holes die young. That single fact transforms the Planck star proposal from a theoretical abstraction into a countdown. Stellar mass black holes carry enough mass to stretch the bounce replay across timescales that dwarf the age of the cosmos. Replay durations so long that no telescope pointed at a stellar collapse will ever capture the final frame. But mass scales downward, and the replay timer scales with the mass. Cut the mass, and the clock accelerates. Cut the mass far enough, and the clock matches the age of the universe. Right there, at that boundary, the abstraction ends. The observable consequences begin. The threshold sits at roughly 10 to the power of 14 grams. Above that mass, the exterior bounce takes longer than the cosmos has existed, and the black hole is still replaying. Below that mass, the bounce has already finished, and the white hole that emerged released a burst of energy into a universe that had no name for the flesh. Between those two boundaries, a narrow band of masses occupies the transition zone, black holes whose bounces are completing during the present epoch, the same epoch where instruments sweep the sky and record every transient flash arriving from deep space. The mass range is not large. 10 to the power of 14 grams to 10 to the power of 16 grams spans a window roughly 100 times wide. But inside that window, the oldest detonations in the cosmos are finishing. The explosions are not future events. The explosions are current events happening in the same era where data archives grow by terabytes every night. Rovelli and Vidotto derived the bounce duration as a function of mass. The exterior wait time scales with the square of the mass, multiplied by a small geometric constant near 0.05, all measured in Planck units. For a black hole with one solar mass, the weight exceeds the projected lifetime of every structure in the observable universe. For a black hole with the mass of a mountain, roughly 10 to the power of 15 grams, the duration drops to approximately the current age of the cosmos, somewhere near 14 billion years. The calculation does not require exotic assumptions. The formula follows from the tunneling probability that governs the black to white transition in the Haggard and Rovelli metric. Compress the quantum region of the bounce into a finite space-time volume. Compute the amplitude for the geometry to tunnel from trapped horizon to anti-trapped horizon, and the timescale emerges. The mass-squared dependence is not a fitting parameter. The mass-squared dependence is a consequence of the geometry. And the consequence is that the smallest primordial black holes, the ones born in the first fraction of a second after the beginning of the universe, are the first to finish. The universe manufactured those small black holes in abundance. During the first microsecond of existence, density fluctuations in the hot, compressed plasma were enormous. Regions slightly denser than the surrounding material collapsed under their own gravity before expansion could dilute the excess. No star needed to form first, no fusion reaction needed to run out of fuel. Gravity alone did the work, compressing plasma past the critical threshold, while the cosmos was still too hot and too dense for atoms to exist. The formation mechanism is simple, almost elegant. A patch of the primordial plasma exceeds the local gene's mass, the minimum amount of material needed for gravity to overpower the surrounding pressure and trigger collapse. Once that threshold is crossed, the patch collapses faster than the Hubble expansion can counteract, and a black hole forms before the universe reaches 1 second of age. The black holes that formed were small because the horizon mass scales with the Hubble mass at the moment of formation. During the first microsecond, the Hubble mass was tiny by astrophysical standards, far below a stellar mass. Mountain-scale masses, asteroid-scale masses, compressed into horizons smaller than a proton, yet carrying enough energy to curve spacetime into a trap. Those traps have been running ever since. 14 billion years of silent operation, while the rest of the universe assembled around the containers. Almost 14 billion years of running. And for a black hole at the critical mass, 14 billion years is enough. The replay is ending. The compressed core, which has been sitting at Planck density since the bounce occurred, is pushing through the final phase of the slow-motion transition. From the perspective of the matter inside, the journey ended before a photon could cross an atom. From the perspective of every telescope on the planet, the white hole emergence is happening now. The first galaxies formed roughly 400 million years after the beginning. The first stars ignited before the galaxies even took shape, burning through hydrogen fuel in isolation across an empty, structureless cosmos. 2 billion years of mergers and collisions assembled the earliest large-scale structures. 5 billion years in, the first heavy elements forged inside dying stars seeded the raw material for rocky planets. 9 billion years passed before the sun condensed from a rotating cloud of gas and dust. Earth solidified 500 million years after the sun. Life appeared on Earth within the first billion years of the planet forming. The first organisms complex enough to leave fossils arrived 3.5 billion years later. Homo sapiens arrived 300,000 years ago. Roughly 12,000 years ago, agriculture took root across several continents simultaneously. 5,000 years ago, the first written records appeared in Mesopotamia, and the slow accumulation of human knowledge began. Less than 200 years ago, the first photograph froze a single moment of light onto a metal plate, and within decades, the telegraph carried messages across the Atlantic Ocean at the speed of electricity. Darwin published On the Origin of Species, rewriting the story of life on this planet, while every primordial clock in the critical range kept counting. The Wright brothers flew at Kitty Hawk, and within 40 years of that first 12-second flight, world wars had consumed entire continents. Humanity split the atom. Then humans used that knowledge to build weapons capable of erasing cities in a single flash. 68 years ago, the first satellite reached orbit. A human stepped onto the surface of another world. 56 years ago. 80 years ago, the first radio telescope pointed at the sky. And during all of that time, every primordial black hole in the critical mass range has been counting down. Every clock in the critical range started before stars existed. Those clocks continued while the first galaxies assembled, while the Milky Way took shape, while the solar system condensed from a cloud of gas and dust. Never once did the counting pause. Galileo aimed a telescope at Jupiter, and Einstein wrote the field equations that describe gravity itself. Through every milestone, the clocks kept running. Silently, the countdown has been running, and for the smallest objects in the critical range, the counter has reached zero during the era of human civilization. No remote future is involved. Instead, the detonation is a prediction about the present, a statement that the oldest explosions in the universe are finishing right now. During the same decades where radio dishes record the sky and satellites catalog every gamma ray arriving from beyond the atmosphere. The energy budget of the flash is staggering given the source. Every primordial black hole that finishes the bounce releases the majority of the energy that fell in at formation. Hawking radiation bleeds some mass during the long exterior wait, but if the bounce completes before the Hawking process consumes the entire mass, the core retains memory of the original collapse. Memory survives inside the Planck star, and nothing about the original mass is forgotten. That memory determines the explosion. A primordial black hole with an initial mass near 10 to the power of 14 grams carries roughly 10 to the power of 47 ergs of total energy. All of that energy concentrates in a region smaller than a wavelength of visible light. To put that number into scale, the total energy output of the sun, over 10 billion years of hydrogen fusion, amounts to roughly 10 to the power of 51 ergs. A single Planck star explosion releases 1/10,000th of the total lifetime energy of a star. Imagine a camera flash that contained the energy of a small nuclear detonation, compressed into a single burst lasting less than the blink of an eye. The Planck star explosion is that flash, except the energy source is not a battery or a nuclear reaction, but the gravitational potential of matter that has been falling for almost 14 billion years. The largest hydrogen bomb ever detonated, the Tsar Bomba, released roughly 10 to the power of 24 ergs. A single Planck star explosion dwarfs the most powerful weapon humanity has ever built. The difference is not close, roughly 10 to the power of 23 times more energy than the Tsar Bomba contained, released in a single burst. And the explosion arrives not as a spreading fireball, but as a focused burst traveling at the speed of light, carrying every signature of the mass that produced the detonation. All of that energy compressed into milliseconds. When the anti-trapping horizon forms and the white hole releases the stored material, none of that energy trickles out slowly. Fast and violent, the release is constrained to a burst whose duration is set by the light crossing time of the emerging object. For a black hole at the critical mass, the Schwarzschild radius at the moment of emergence corresponds to a wavelength in the infrared to radio range. Baru, Rovelli and Vidotto computed the expected signal in 2014. One component of the burst, the lower energy signal produced by the size of the emerging white hole, falls at a wavelength near 0.02 centimeters deep in the radio band. A second higher energy component, produced by the particle payload liberated from the quantum gravitational core, extends into the gamma ray range around 10 megaelectron volts, two signals from one explosion, a radio flash and a gamma ray flash arriving simultaneously from the same point in the sky, each carrying a distinct fingerprint of the mass that produced the burst. The prediction contained a detail that no other model in astrophysics could replicate. Because the signal wavelength depends on the mass of the exploding black hole, and the mass depends on when the black hole formed, signals arriving from greater distances come from black holes that formed later, and therefore had less time to run. Later formation means smaller initial mass, smaller horizon at emergence, and shorter wavelength at the source. But greater distance also means greater cosmological redshift, which stretches the wavelength. For ordinary astrophysical sources, distance always increases the received wavelength. For Planck star explosions, the two effects compete. The youth of distant sources pushes the emitted wavelength shorter, while the expansion of the universe stretches the received wavelength longer. Barrow and Rovelli showed that these two effects nearly cancel. The received wavelength flattens at large distances, producing a signature that no ordinary explosion can mimic. A standard gamma ray burst gets redshifted normally. So does a standard radio transient. But a Planck star burst shows a characteristic flattening in the wavelength-distance relation that is unique to the bouncing black hole model. That flattening is a prediction. Before any data existed, the math described the pattern, and the prediction has not yet been tested because no observatory has yet searched for the specific combined signature, simultaneous radio and gamma ray bursts with the predicted wavelength-distance relation. While the signal prediction sat untested, a separate question emerged from the same framework. In 2025, Oim Trivedi, a graduate student at Vanderbilt University, and Abraham Loeb, a professor at Harvard, asked what dead black holes leave behind. Every completed bounce produces a stable remnant at the Planck mass. Those remnants do not radiate. Light passes through without interaction. Only gravity connects the remnants to the rest of the cosmos. Cold, dark, stable, and abundant, the remnants behave exactly like dark matter. Every observational constraint was satisfied. For a brief moment, the Planck star framework had produced the most elegant dark matter candidate in decades, one requiring no new particles, no new forces, nothing beyond general relativity and quantum gravity applied consistently. Then Trivedi destroyed the proposal from the inside. Within the same year, Trivedi and Loeb showed that producing enough primordial black holes to generate the required remnant density would create gravitational waves too strong for LIGO to have missed. The detector found nothing. The simplest version of the dark matter pathway collapsed, killed by the same graduate student who proposed the pathway. A door slammed. A narrower window opened. Non-standard formation pathways survive, but the clean version died under the weight of honest analysis. None of that touches the core prediction. Whether or not the remnants explain dark matter, the bounces are still happening. Primordial black holes at the critical mass are still finishing the replay. Bursts are still predicted. Dark matter questions and signal questions occupy different branches of the same framework, and the collapse of one branch leaves the other standing. One branch asks what dead black holes leave behind. Another branch asks what the death itself looks like. LIGO constrained the remnants. Nothing has constrained the signals. And somewhere in the archives of radio observatories around the world, years of data sit waiting, unexamined for the specific signature that Barrow and Rovelli describe. Already, the data might contain the flashes. No new telescope is required. Not a single new detector needs to be built. Zero funding proposals need to survive a committee review. If those signals exist, the signals have been arriving for years, recorded by instruments designed for other purposes, filed alongside millions of other transient events, catalogued by automated software that was never programmed to recognize the combined radio and gamma signature of a dying black hole. Perhaps the answer sits on a hard drive at a radio observatory, buried under petabytes of pulsar surveys and calibration logs, waiting for someone to run the right search query. Perhaps the most consequential discovery in quantum gravity does not require a new experiment. No billion-dollar detector is required, and no decade-long construction project needs to break ground. No launch window. What might be needed is a graduate student, a laptop, and access to an archive that already exists. A first candidate arrived before anyone was looking. On November 2nd, 2007, Duncan Lorimer, an astrophysicist at West Virginia University, and a graduate student named David Narkovich were sifting through archival data from the Parkes radio telescope in New South Wales, Australia. For years, the Parkes dish had been surveying the sky for pulsars, rapidly spinning neutron stars that emit regular radio pulses like cosmic lighthouses. Lorimer and Narkovich were searching the data for new pulsars when a single event stopped the analysis. A burst of radio energy lasting roughly 5 milliseconds had arrived from a direction that pointed well outside the Milky Way. 5 milliseconds. Shorter than the time between two heartbeats. Shorter than the duration of a single spoken syllable. Yet the energy packed into those 5 milliseconds dwarfed anything a nearby source could produce. Dispersion in the signal, the way different frequencies arrived at slightly different times, after traveling through the ionized gas between galaxies, indicated that the burst had traveled billions of light years to reach the detector. Energy was enormous for a radio event. Duration was absurdly short. Nothing in the catalogue of known astrophysical sources produced a signal with that combination of distance, energy, and brevity. Every previous radio transient had a known origin, a pulsar, a flare star, a magnetized plasma event within the Milky Way. The Lorimer burst matched none of those categories. The burst was alone, unprecedented, and unexplained. Without knowing what category to assign the signal, Lorimer and Narkovich had stumbled onto the first fast radio burst. Immediate confusion followed. A single burst, observed once, from an unknown source at cosmological distance, with no repeat and no identified counterpart at any other wavelength. Across the astrophysics community, debate erupted over whether the signal was real or an instrumental artifact. Some suspected terrestrial interference. Suspicion had precedent. In 2010, researchers at Parkes identified a series of bursts that appeared to come from space, but were actually caused by a microwave oven in the staff kitchen. Staff members had been opening the oven door before the heating cycle finished, producing a burst of radio frequency interference that the telescope dutifully recorded. Famous in radio astronomy circles, the Periton events, as the microwave signals were named, cast a shadow over every subsequent burst detection at Parkes. The discovery by Lorimer sat under that shadow for years, dismissed by skeptics as another instrumental ghost. Lorimer did not waver. The dispersion measure of the burst, the precise way the radio frequencies had spread apart during their journey through intergalactic space, pointed to a source billions of light years away. No microwave oven could produce that dispersion pattern. No terrestrial source could mimic the signature of a signal that had traveled through the ionized medium between galaxies. The data told one story. The skeptics told another. For 5 years, the skeptics held the floor. The skeptics were wrong. A second burst appeared in archival data from the Arecibo Observatory in Puerto Rico in 2012. The Arecibo dish, 305 meters wide, built inside a natural limestone sinkhole in the mountains of northwestern Puerto Rico, operated independently from Parkes. Built on a different continent, operated by a separate team, running an entirely independent detection pipeline and pointing at a completely different part of the sky. Same kind of signal. Millisecond duration, cosmological distance implied by the dispersion. The phenomenon was not a Parkes artifact, and every independent detection confirmed the reality of the signal. By 2013, 4 more bursts had been identified, all from different directions in the sky, all at cosmological distances, all lasting milliseconds, all refusing to repeat. Timing is striking. Rovelli and Vidotto calculated the expected signal from an exploding Planck star in 2014. Data containing the Lorimer burst was recorded in 2001, discovered in 2007. 7 years separated the detection from the prediction, but the prediction was made without knowledge that the prediction matched an observed phenomenon. Wavelength of the Lorimer burst sits in the range that the Planck star model predicts for a primordial black hole near the critical mass. Duration, milliseconds, matches the light-crossing time of the emerging white hole. Energy, concentrated in a single, non-repeating flash from a cosmological distance, matches the expected profile of a one-time detonation, rather than a repeating engine like a pulsar or a magnetar. Nobody is claiming the Lorimer burst was a Planck star explosion. Evidence is circumstantial. Only a single data point exists, one flash from one direction with no counterpart. But the coincidence persists. Physicists described a predicted signal, and that exact type of signal exists in the observational record. Properties overlap, and the prediction was made independently years after the first observation, without reference to fast radio bursts. 2 groups of physicists working on unrelated problems on different continents converged on a signal that matched in wavelength, duration, energy, and the cosmological distance implied by the dispersion measure. Convergence alone is not proof, but convergence of this specific kind, where the prediction arrived before the observation and was constructed without any reference to the data, carries a weight that post hoc fitting cannot match. A model built to explain existing data can always be tuned to fit. A model that describes a signal before the signal is found has no tuning to hide behind. In the history of physics, the predictions that arrive before the observations have a disproportionate track record of turning out to be correct. Dirac predicted antimatter before the positron was found, and Pauli predicted the neutrino before any detector confirmed a single one. Einstein predicted gravitational waves a full century before any instrument could feel the ripple. Prediction before observation does not guarantee correctness, but prediction before observation earns a hearing that post hoc explanations cannot claim. Since 2007, the catalog of fast radio bursts has grown from one event to over 600. Some bursts repeat from the same location, others flash once and vanish forever. The 2 populations may represent entirely different engines producing the same kind of signal. Most remain unexplained, and here is what makes the catalog dangerous for the Planck star question. In 2020, a magnetar inside the Milky Way produced a burst, confirming that highly magnetized neutron stars are one source. But that confirmation applied to one local event from one known object. The distant bursts, the ones arriving from billions of light years away, the ones that never repeat, remain without a confirmed source. Hundreds of non-repeating flashes from cosmological distances sit in the catalog, recorded by instruments around the world, arriving at a rate of thousands per day across the entire sky, each one lasting milliseconds and then vanishing without a trace. If even a small fraction of those non-repeating, cosmologically distant bursts originate from Planck star explosions, then the data already contains the signature of the oldest objects in the universe, dying. Archives hold the evidence. No dedicated search has begun. A prediction from 2014 describes exactly the kind of signal, that fills the unexplained portion of that catalog, and the clocks that would produce those signals have been running since before the first star ignited, counting down toward a moment that might have already arrived. Now we can talk about what actually arrived. The calculation sat on paper for 7 years before anyone connected the math to the sky. Barrow, Rovelli, and Vidotto described the signal in 2014. The description was precise. Wavelength in the radio band, near 0.02 centimeters, determined entirely by the Schwarzschild radius of the emerging white hole at the critical mass. A second component extending into the gamma-ray range, near 10 megaelectronvolts, determined by the particle payload trapped at Planck density since the original collapse. Both components arriving simultaneously from the same point in the sky. Duration set by the light crossing time of the emerging object measured in milliseconds. Energy consistent with the total gravitational potential of a primordial black hole, near 10 to the power of 14 grams, roughly 10 to the power of 47 ergs, all compressed into a single flash. The forecast was specific. The forecast was falsifiable. And the forecast was made without any reference to the catalogue of unexplained radio events accumulating since 2007. Two separate threads of physics had been developing on opposite sides of the discipline for years. On one side, a small group of quantum gravity researchers in Marseille, Grenoble, and Nijmegen had been calculating what a dying black hole would look like from the outside. On the other side, radio astronomers in Australia, Puerto Rico, and North America had been cataloguing millisecond flashes from deep space, flashes that no known source could explain. Neither group referenced the other. Neither group attended the same conferences. Not a single overlapping citation appeared in the combined bibliography. The mathematical description described a signal. The observation recorded a signal. Two communities working on unrelated problems had converged on the same kind of event without speaking a word to each other. The question that remained was whether those two signals described the same physical phenomenon. The thread from quantum gravity ran through a clean chain of reasoning. Start with the Rovelli and Vidotto proposal from 2014. Matter collapses, hits the Planck density floor, bounces. Haggard and Rovelli constructed the space-time metric, describing the transition from trapping horizon to anti-trapping horizon. The exterior geometry connects to the Einstein equations without violating any classical constraint. No exotic matter is required. No new particles appear. The only departure from classical physics occurs inside a compact region at the core. There, quantum gravitational effects replace the singularity with a finite bounce. The duration of the bounce, as measured by an exterior clock, scales with the square of the mass, multiplied by a geometric constant near 0.05. For a black hole at the critical mass, roughly 10 to the power of 14 grams, the exterior wait time matches the current age of the cosmos. Upon completion, the white hole releases a flash. Barrow then joined Rovelli and Vidotto to calculate the full set of observable properties. The calculation proceeds from the geometry, not from adjustable parameters. At the emerging object, the Schwarzschild radius sets the wavelength of the lower energy component. The trapped particle payload sets the energy of the higher energy component. No fitting is performed, no free parameters are tuned to match any data. Every property of the signal follows from the physics of the bounce, the mass at the critical threshold, and the general relativistic geometry of the emerging white hole. The result is a two-component signal, radio and gamma ray, arriving together from a single point, lasting milliseconds. The thread from radio astronomy ran independently, and the catalogue grew without any theory to explain the growth. In 2001, the Parkes radio telescope in New South Wales recorded a 5-millisecond flash of concentrated radial energy on a single pass of the sky. Nobody noticed. The data sat buried in archival storage for 6 years because the automated pipelines were built to find pulsars, periodic signals that repeat with clockwork precision. Nobody had programmed the software to flag a single, non-repeating event. In 2007, Duncan Lorimer an astrophysicist at West Virginia University, and a graduate student named David Narkovich reprocessed the old data with a new algorithm, one designed to catch solitary flashes instead of regular pulses. A single event surfaced from the noise. 5 milliseconds of radio energy arriving from well outside the plane of the Milky Way with a dispersion pattern that indicated a source billions of light years away. Nothing in the existing catalog explained the event. Nothing came close. Skeptics had dismissed the signal as instrumental noise, until independent detections at Arecibo and other observatories confirmed that the phenomenon was real. By 2020, more than 600 millisecond flashes had been recorded from deep space, arriving from every direction, each carrying energy that dwarfed anything a local source could produce. Some repeated from the same location. Others fired once and vanished forever. Thousands of these flashes arrive across the entire sky every day, recorded by dishes and arrays built for entirely different purposes, filed alongside pulsar surveys and calibration logs, processed by automated pipelines scanning terabytes of raw radio data every night. The signals had a name. Fast radio bursts. The signals did not have a confirmed origin. Here is where the two threads meet. The description from 2014 specified a signal with exact properties. Wavelength in the radio band, duration measured in milliseconds, energy consistent with a primordial detonation. A single, non-repeating flash from billions of light years away. The Lorimer event, recorded in 2001 and discovered in 2007, matches every one of those properties. Received wavelength lands where the bouncing black hole geometry places the lower energy component, or a primordial object near the critical mass. Duration matches the light crossing time that the Haggard and Rovelli metric produces at the corresponding Schwarzschild radius. And the energy budget matches a bounce releasing 10 to the power of 47 ergs, all concentrated in a single millisecond. That flash arrived from a distance consistent with the source, one that formed in the first fraction of a second after the beginning, and took nearly 14 billion years to finish the bounce. And every property of the signal was locked by the geometry before anyone knew such signals existed. No parameter was free, and no adjustment was possible after the fact. The entire framework arrived sealed. Nobody is claiming the Lorimer event was a Planck star explosion. The evidence remains circumstantial. One flash, one direction, no counterpart at any other wavelength. But the structure of the coincidence demands a closer look, because the coincidence has a property that most matches do not. The Planck star framework contains 0 adjustable parameters. Not one. Signal wavelength was not chosen to match the Lorimer event. Duration was not tuned to fit the millisecond window, and the energy budget was not adjusted after the catalog appeared. Every observable property followed from the geometry of the bounce, the mass at the critical threshold, and the Schwarzschild radius of the emerging white hole. Remove the observation entirely, and the framework produces the same numbers. Description preceded knowledge, and no part of that description could have been modified to improve the fit, because no part was adjustable. That structural rigidity separates the Planck star framework from models that can be tweaked after the fact. A flexible model earns suspicion proportional to the flexibility. A rigid framework earns attention proportional to the match. The burden shifts. What remains is no longer whether the framework could be right. Rather, the question is whether the framework can be excluded by the evidence that already exists. Then, in 2020, one thread appeared to snap. A magnetar inside the Milky Way, designated SGR 1935 + 2154, released a millisecond radio flash that instruments captured in real time. The magnetar sits roughly 30,000 light-years from Earth, a highly magnetized neutron star with a surface field strong enough to rip apart atoms at a distance of 1,000 kilometers. The event matched the general characteristics of fast radio bursts: millisecond duration, concentrated radio energy, enormous power relative to the source distance. For the first time, a known object in a known location had produced a known signal. One origin was confirmed. Magnetars generate fast radio bursts. The confirmation ended years of speculation about at least one class of origin. The celebration was earned. But the celebration carried a quiet limitation that most summaries did not mention. The magnetar flash came from inside the galaxy. The energy of that flash, while staggering by galactic standards, fell orders of magnitude below the energy carried by extragalactic signals, arriving from billions of light years away. Distance matters for the physics as much as for the detection. A candle flame and a thermonuclear detonation both produce photons, but nobody would argue that both share the same engine. The magnetar conformation proved that highly magnetized neutron stars can produce millisecond radio flashes detectable at galactic distances. That conformation did not explain the events arriving from distances spanning billions of light years, with energies that dwarf the galactic detections by factors of thousands or more. The distant population remains a separate problem, with a separate energy budget and a separate origin that has not been identified. Both investigations collide at precisely this gap. The magnetar inquiry traced one origin story: a neutron star with a magnetic field measured in billions of Tesla, releasing energy in concentrated flashes that crossed the Milky Way. That origin is confirmed, grounded in observation, supported by simultaneous detection at multiple wavelengths. That origin explains one class of events from one type of source at galactic distance scales. The Planck star proposal opens a second origin story: a primordial black hole formed during the first microsecond of the universe, running a silent countdown for almost 14 billion years, finishing the bounce during the same era where radio telescopes sweep the sky, and releasing a flash that carries the gravitational potential of the original collapse, compressed into a single millisecond. Two sources, two mechanisms, separate eras of formation divided by the entire history of the universe, both producing millisecond radio signals. The magnetar confirmation did not close the case on all fast radio bursts. Only one class was settled. The distant, non-repeating events remain open, and the non-repeating characteristic matters deeply for a specific reason. A magnetar is a stable engine that persists after releasing a flash. The magnetic field replenishes. Another flash can follow, and another and another. Some fast radio bursts do repeat from the same location, behavior entirely consistent with a persistent engine that fires multiple times. But a Planck star explosion is a one-time detonation. The black hole finishes the bounce, the white hole emerges, the signal is released, and the object no longer exists. One flash, one direction. No source remains to fire again. The non-repeating detections in the catalog behave precisely as a population of one-time detonations would behave. No engine survives, no source persists. Hundreds of single flashes from distances spanning billions of light years, each lasting milliseconds, each vanishing without a trace, each refusing to repeat, no matter how long the telescope keeps watching. Consider what that catalog looks like from above. Hundreds of non-repeating events scattered across the sky, arriving from every direction, each one a solitary flash at extreme distance. Some arrived from the direction of ancient galaxy clusters. Some arrived from voids between filaments of the cosmic web, regions where almost nothing visible exists. The distribution is isotropic, spread uniformly as though the sources were embedded throughout the entire observable volume of the universe at random. A population of magnetars would cluster near galaxies because magnetars are born from massive stars, and massive stars form inside galaxies. A population of dying primordial black holes would be scattered everywhere because primordial black holes formed from density fluctuations in the plasma that existed before galaxies, before stars, before large-scale structure of any kind. The distribution of non-repeating detections does not obviously track galaxy populations. Whether that isotropy is significant or merely reflects the limited sample size remains an open question, but the pattern is consistent with a source population that predates galactic structure, and primordial black holes are the oldest structured objects in the cosmos. And the convergence between theory and observation sharpens further when the non-repeating population is examined against the broader sky. Every non-repeating detection shares a set of properties that the repeating population does not. Non-repeaters arrive once, carry higher average energy than repeaters, and show dispersion measures consistent with sources at extreme distances. Repeaters cluster near identified host galaxies, behaving as persistent engines rooted in galactic structure. Non-repeaters scatter uniformly across the sky, arriving from every direction without preference for any galactic neighborhood. That pattern suggests sources that formed before galaxies existed, embedded in the primordial fabric of the cosmos before large-scale structure took shape. If the non-repeating population represents a distinct class of origin, the observed properties match the expected behavior of primordial black holes finishing the bounce. Solitary, one-time events from distances that predate large-scale structure, each carrying an energy budget set by the gravitational potential of a mass that collapsed in the first microsecond. The possibility that two entirely different engines produce the same kind of signal is not unprecedented in astrophysics. Gamma-ray events were once assumed to have a single origin. Decades of observation revealed two populations: short gamma-ray events produced by neutron star mergers and long ones produced by massive stellar collapses. The division took years of data and multiple independent lines of evidence to establish. Fast radio bursts might be following the same trajectory, one population from magnetars, another from a source that has not yet been identified. The magnetar confirmation did not close the mystery. Instead, the confirmation opened a sharper and more precise version of the mystery, one that had been sitting unanswered for years. What produces the distant, non-repeating flashes that no magnetar can explain? The Planck star framework contained a detail that no competing model can reproduce, and no observatory has yet tested. Barrault and Rovelli showed that the wavelength-distance relation for bouncing black hole signals flattens at large distances. For every ordinary astrophysical source, greater distance means greater redshift from cosmic expansion, which means the received wavelength always increases with distance. A gamma-ray event gets redshifted. A standard radio transient gets redshifted. The relationship between wavelength and distance follows a predictable curve set by the expansion history of the universe. For Planck star signals, two competing effects cancel. More distant signals come from black holes that formed later in the first fraction of a second, with smaller initial masses producing shorter wavelengths at the source. Cosmic expansion stretches those shorter wavelengths back toward longer values. Barrault and Rovelli demonstrated that these two effects nearly neutralize across a wide range of distances. The result is a characteristic flattening in the wavelength distance curve, a signature unique to the bouncing black hole model, a pattern that no magnetar, no pulsar, no gamma-ray event, and no known astrophysical engine can replicate. That flattening is not a vague tendency. Rather, the flattening is a quantitative curve with a specific shape, derivable from the mass distribution of primordial black holes, from the tunneling probability that governs the bounce, and from the expansion rate of the cosmos. Any population of bouncing black holes with a known mass spectrum would produce a specific footprint in a wavelength distance plot. That footprint would look nothing like the smooth, monotonic redshift curve that every ordinary source follows. Instead, the curve would plateau. Signals from nearby sources and signals from sources billions of light years away would arrive at similar wavelengths, clustered in a narrow band that the mass spectrum determines. No fitting is required to generate the curve. Physics alone dictates the shape, and the shape is testable against the existing catalog. A graduate student with access to the fast radio burst catalog could plot received wavelength against estimated distance for every non-repeating detection and search for the plateau. If the plateau exists, no known astrophysical mechanism can produce the pattern. If the plateau does not exist, the Planck star origin for fast radio bursts is ruled out. One plot, one decisive test. Either the plateau appears, confirming a signal that no known engine can mimic, or the plateau does not appear, and the Planck star origin collapses under the weight of absent evidence. The test has never been run. No observatory has conducted the search, and no research group has submitted a proposal to begin. Not because of any technical barrier, and not because the instruments are missing or the data has been lost. Every archive needed already holds the raw observations. The reason is straightforward. Nobody has connected the quantum gravity literature to the fast radio burst detection pipeline. Two communities occupy opposite ends of the physics department, separated by hallways and conference schedules and citation networks that never overlap. Quantum gravity researchers publish in journals that radio astronomers never open. On the opposite side of the building, radio astronomers catalog detections in databases that no one studying quantum gravity has ever queried. The gap is not intellectual. The gap is institutional. What the search requires is simple: one person willing to cross that hallway. The specific combined signature, simultaneous radio and gamma ray emission, arriving from the same point with the characteristic wavelength distance flattening, has never been targeted by any instrument on any continent. Archives at Parkes hold years of raw data. The Canadian Hydrogen Intensity Mapping Experiment in British Columbia processes thousands of detections per year. The 500-meter aperture spherical telescope in Guizhou, China, the largest single-dish radio telescope on the planet, has been accumulating fast radio burst detections since operations began. Every one of those instruments recorded data using pipelines optimized for known source types. Not one searched for the specific combined signature that the Planck star framework describes. And the most consequential discovery in quantum gravity might not require a single new experiment to be built. No billion-dollar detector needs to be commissioned. Not a single decade-long construction project needs to break ground. No launch window needs to be scheduled for any new satellite or observatory. All that stands between the question and the answer is a single search query run against data that has been sitting on hard drives for years, waiting for someone to ask. The convergence between the quantum gravity framework and the radio astronomy catalog is not proof. Proof requires the specific test that Barrow and Rovelli described, a systematic search for simultaneous radio and gamma ray emission with the characteristic wavelength distance flattening. Until that search is conducted, the overlap between the mathematical description and the observed signals remains a coincidence, one that might be meaningful or might be accidental. But the coincidence is precise, and the calculation arrived first. The clocks that produced these signals started counting before the first hydrogen atom formed. The signals, if the signals exist, have already arrived, and somewhere in the unexplained fraction of the fast radio burst catalog, the death of the oldest objects in the universe might already be on record. Nothing in the universe lasts forever. Stars burn out after billions of years of steady fusion. Galaxies collide and merge. Protons, the most stable building blocks of matter, may themselves decay on timescales so vast that no clock could measure the duration. But black holes were supposed to be the exception, the one permanent fixture, the ending that nothing could reverse. And the ending turned out to be a storage receipt. Every result in this investigation points to the same conclusion, and the conclusion is not subtle. No crushing point was ever real. A bounce finishes in microseconds from the inside. Outside, the replay stretches across billions of years, and the oldest replays are finishing now. Predicted signals match unexplained flashes already sitting in observatory archives. Two separate lines of physics, one from quantum gravity and one from radio astronomy, converged on the same kind of event without sharing a single citation. None of those results have been overturned. None have been tested with the specific combined signature the framework describes. And every one of those results rests on a single foundation: the universe does not allow permanent destruction. That claim deserves scrutiny, because the claim carries consequences far beyond black holes. The claim rewrites the relationship between the universe and everything the universe contains. If permanent destruction is impossible, then the cosmos operates on a principle that most humans have never considered. Loss is a temporary condition, imposed by the difference between two clocks, not by the nature of reality. If the bounce is real, then every black hole that has ever formed is a temporary container. Every stellar mass black hole, every supermassive engine at the center of every galaxy, every primordial remnant formed before the first atom existed, is running a slow-motion replay of a bounce that already finished on the inside. The material consumed at the beginning of the cosmos has not been destroyed. The material sits compressed at maximum density inside an interior geometry that has been growing for billions of years. quietly expanding behind a horizon that no external instrument can penetrate. Nothing was lost. The contents are still there. Rovelli described the invocation directly in the 2024 review. Information follows a different path from energy. During the long evaporation process, Hawking radiation carries energy away from the horizon, slowly bleeding mass from the exterior. That radiation is genuinely thermal, genuinely random, carrying no record of what fell in. Energy escapes. Information does not. Instead, the quantum correlations that encode the identity of every particle, every photon, every piece of matter that crossed the horizon remain trapped inside the growing interior. The interior volume stretches linearly with time, adding room proportional to the square of the mass, year after year, while the exterior shrinks. A black hole that formed 10 billion years ago possesses an interior geometry so spacious that the volume dwarfs anything the exterior universe contains at comparable scales. That interior is not empty. The interior is a library. Every quantum state that entered the horizon is preserved inside the growing chamber, encoded in the entanglement structure of the trapped radiation. And that library does not burn. The Hawking radiation escaping to infinity is entangled with negative energy radiation that fell inward, and the inward component carries the correlations that purify the total state. A 40-year crisis, the information paradox that fractured theoretical physics into warring camps, dissolves. Not through exotic mechanisms at the horizon, not through firewalls or holographic reconstructions or wormholes threading the geometry of space-time. Instead, the resolution is architectural. Enough room exists inside. Quantum states fit inside a volume that classical reasoning never computed because nobody ran the calculation until 2024. No paradox ever existed. What looked like an impossible contradiction was a failure to check the interior geometry of the container. Consider the scale of that oversight. For 4 decades, physicists debated whether information survives inside a black hole. Entire careers were built around the question. Leonard Susskind and Gerard Tooft developed the holographic principle, partly in response to the crisis. Juan Maldacena constructed the most studied correspondence in theoretical physics, linking gravity in curved space to quantum field theory on a flat boundary, and one motivation was the information puzzle. The argument consumed conferences, split departments, generated thousands of papers. All the while, the interior volume was growing in plain sight, computed by equations that a graduate student could verify, and nobody checked. Rovelli called the oversight a consequence of looking only outward. Nobody ran the calculation. The equations were available for decades, and the tools were straightforward. But the exterior dominated every conversation, and the geometry behind the horizon went unchecked. But the resolution carries a cost that nobody anticipated. When the bounce finally completes and the white hole emerges, what comes out? The material is conserved. Quantum mechanics guarantees unitarity, the principle that no information is ever destroyed in the fundamental equations. Every particle state that crossed the horizon is preserved somewhere in the global quantum state of the system. Conservation holds across every equation. Completeness holds. Not a single quantum number was erased. And yet, the form of the return is unknown. Rovelli and Vidotto estimated the remnant lifetime at roughly the 4th power of the original mass. For a black hole that started with 10 solar masses, that duration exceeds every meaningful timescale in the observable universe by factors beyond naming. The remnant sits at the Planck mass, a few millionths of a gram, stabilized by the area gap that loop quantum gravity predicts, the minimum non-zero area that a horizon can possess. Below that area, no black hole and no white hole can exist. The geometry forbids a smaller horizon. And so the remnant persists, trapped in a quantum superposition of black and white hole state, indistinguishable from either geometry when observed from the outside. A coin spinning between two faces, never landing, radiating the stored information in quanta so low in energy that each photon carries barely a whisper of the original material. The emission process is agonizingly slow. To release a large amount of information using only a small energy budget the remnant must emit an enormous number of very low-frequency photons. Low frequency means long wavelength, and long wavelength means a drawn-out emission window. The remnant does not explode. The remnant whispers, releasing the contents of the library one photon at a time, each photon stretched to wavelengths far beyond what any current instrument could detect. Total emission time scales with the fourth power of the original mass. For a stellar black hole, the whisper lasts longer than the projected lifetime of all structures in the observable universe. Every star will have burned out, every galaxy will have dispersed, before the remnant finishes returning the contents of a single stellar collapse. The universe keeps the receipt, but the delivery takes longer than the universe itself. Ohm Trivedi and Abraham Loeb confronted one consequence of that delivery schedule in 2025. If every dead black hole leaves behind a Planck mass remnant, and if primordial black holes produced enough remnants to fill the cosmos, then those remnants could account for all the missing mass. Cold, stable, invisible to every detector except gravity. Every observational constraint on dark matter was satisfied. Remnant populations matched the required density on the first attempt, without invoking a single particle or force that physics had not already confirmed. Too clean to ignore, too simple to survive without challenge. Trivedi destroyed the proposal from inside the same collaboration. The intellectual honesty required to dismantle your own discovery within the same year you publish the discovery is rare in any field. Rare is still in a field where careers are built on proposals that survive peer review, not on proposals that self-destruct under honest analysis. Within months of publishing the proposal, Trivedi ran the formation rates against the detector constraints. Standard density fluctuations in the early universe, under ordinary conditions, would have produced gravitational ripples far above the sensitivity threshold. Silence at the detectors ruled out the cleanest version of the pathway. At Hanford and Livingston, during the third observing run, gravitational wave measurements killed the simplest formation pathway. Required signals exceeded the measured upper limit by factors of 10 to 1,000. But the door did not close all the way. Non-Gaussian primordial fluctuations, distributions with fatter tails or sharper peaks than the standard bell curve, can produce the same number of primordial black holes while generating gravitational waves below the LIGO threshold. The required power spectrum drops from 10 to the -2 to 10 to the -3, a reduction large enough to satisfy the constraint. Exotic formation channels survive. The pathway is narrower, more constrained, less elegant. But the pathway exists, and the remnants themselves, whether or not the remnants account for dark matter, are still predicted by the framework. Every completed bounce still produces a stable object at the Planck mass. Those objects still populate the cosmos. LIGO answered only how many of those remnants populate the cosmos, not whether the remnants exist at all. Roger Penrose proposed a name for these objects: Erebons, named for Erebos, the Greek god of darkness. Small enough to pass through ordinary matter without disturbing a single bond between atoms. Massive enough to curve space-time at close range. Cold enough to emit no detectable radiation on any timescale shorter than the lifetime of the cosmos. Invisible by every standard definition, Penrose argued that these particles, if abundant enough, would fill the universe as a dark component, impossible to distinguish from any other cold, dark matter candidate. The name has not caught on in the broader community, but the concept persists. A graveyard full of objects too small to see, too stable to decay, too quiet to detect, carrying inside their Planck-scale horizons the complete quantum history of every black hole that ever lived and died. Right now, billions of these remnants, if the remnants exist, may be drifting through the same galaxy where human beings argue about their existence, passing through planets, through stars, through the bodies of every person alive, without disturbing a single atom. The matter that built the first structures in the universe, compressed and bounced and locked inside Planck-scale containers, could be flowing through the room where you are sitting. No instrument would register the passage. No sensor would trigger. The ghosts of the oldest collapses in cosmic history, carried silently in objects smaller than any particle ever measured. And here is the weight of the entire framework, compressed into a single question. If the universe returns everything, Does the return mean anything? The material is conserved. Unitarity guarantees that much. But conservation of quantum information does not mean conservation of meaning. A book burned to ash still contains every bit of information the book originally held, encoded in the exact positions and momenta of every particle of smoke and every photon of heat. The book is recoverable in principle. No physicist disputes that claim. But no technology that will ever exist can reverse the process. The information is present, scattered across a volume of space so large and encoded in correlations so diluted that reconstruction requires tracking every particle in the universe simultaneously, lost in practice. And the universe does not care about the distinction. A black hole does the same to everything the black hole consumes, except the scrambling is more thorough and the container is more patient. Matter falls in, and quantum states preserve every correlation through the entire journey. The bounce reverses the collapse. A white hole emerges, and the material that comes out has been compressed to the densest state the universe allows, held at that density, while the exterior aged billions of years. Released through a channel so narrow, each quantum of information trickles out across timescales that dwarf the lifespan of every structure in the cosmos. The universe technically returns everything. The universe practically erases the story. Hawking spent 30 years insisting that information was permanently destroyed inside black holes. The position was absolute. No hedging, no uncertainty, no escape clause. In 1997, Hawking formalized the claim into a public wager with John Preskill at the California Institute of Technology. If information escapes a black hole, Hawking loses. The bet stood for 7 years. Then, in 2004, Hawking called a press conference in Dublin. Cameras crowded the conference room. Reporters lined the walls. Hawking announced that information survives after all, and handed Preskill a baseball encyclopedia as the agreed prize. Preskill accepted the encyclopedia with visible surprise. Susskind, who had sided with Preskill for decades, noted that Hawking conceded on the right question, but gave the wrong reason. That concession acknowledged that information survives. But Hawking never specified in what form the information survives. One sentence confirmed survival. No sentence described the condition of the survivor. The Planck star framework answers the question Hawking left open, and the answer is not comforting. The book survives. Every page, every word, every letter, encoded in quantum correlations that span the interior geometry of the remnant. But the pages emerge one photon at a time, over durations that exceed the lifetime of every civilization that will ever exist. The library is intact. The librarian is gone. And that is the final image the Planck star proposal delivers. The darkest objects in the universe are not graves. The darkest objects are waiting rooms, patient beyond comprehension, holding every particle that ever crossed the threshold, running in slow motion while the rest of the cosmos ages around the containers. Permanent destruction is something the universe refuses to allow. Every black hole is a temporary phase, and every piece of consumed matter will eventually return. But the return is so slow, so diluted, so stretched across timescales that reduce civilizations to footnotes that the distinction between preservation and loss becomes a question no equation can answer. The matter comes back, the meaning does not. Every image of a black hole ever released to the public carries this revision. Consider the orange ring captured by the Event Horizon Telescope, the shadow of Sagittarius, a star at the center of the Milky Way. The gravitational wave chirps detected by LIGO as two black holes merged. All of those observations documented objects that the public assumed were permanent, endpoints, final answers, places where matter goes and never returns. Every one of those objects, if the Planck star framework holds, is a container in the middle of a countdown. Mergers detected by LIGO did not create a permanent object. Instead, those collisions built a larger container with a longer fuse, a bigger bomb on a slower clock. And the shadow at the center of the galaxy is not a void. Rather, that shadow is a slow-motion replay of a bounce that began billions of years before the solar system formed and will still be replaying long after the sun has burned through every gram of hydrogen fuel. The oldest containers, the ones that formed before the first star ignited, are opening now. Signals may already be arriving. Somewhere in the archives, on a hard drive at a radio observatory in Australia, or a telescope array in British Columbia, or a dish in the mountains of Guizhou, the death of the oldest objects in the universe may already be on record. Bombs built before hydrogen existed, fuses lit before the first galaxy assembled, countdowns hidden behind horizons where no clock visible to the outside could track the progress. Almost 14 billion years of patient, absolute silence. And the silence is ending. Every black hole is a bomb. That sentence opened this story as a provocation, a claim designed to unsettle. Now the sentence returns as a description. The crushing point was never real. A density flaw erased the singularity, and the bounce that replaced the ending has been replaying across two clocks that disagree by billions of years. The oldest replays are finishing now. Predicted signals match unexplained flashes already sitting in telescope archives. One source was confirmed, and the distant flashes still have no name. And if the bounce returns everything, then the darkest objects in the cosmos are not consuming matter. Instead, the darkest objects are holding the material, while the rest of the universe ages around the container. Black holes are temporary. The universe enforces a maximum density, a ceiling that no force can breach. When matter hits that floor, the matter comes back. No singularity was ever hiding at the center. No permanent erasure was ever taking place inside any of those objects. Every black hole that has ever formed, every stellar collapse, every primordial remnant born before the first atom cooled, is a storage container running a slow-motion replay of an event that already finished on the inside. Matter consumed at the beginning of the cosmos is still compressed, behind horizons that the outside universe cannot penetrate. Not a single particle was lost, and nothing was permanently destroyed by the collapse. The contents are still there, but the universe does not promise that the return will mean anything. Unitarity preserves every quantum state. Conservation holds, and the delivery takes longer than every structure in the observable cosmos will survive. Every page in the library is intact, but the librarian is gone. Pages emerge one photon at a time, stretched across wavelengths no instrument will ever detect, released over durations that reduce civilizations to rounding errors. A receipt survives, but the handwriting fades on a timescale that mocks every reader. Preservation and loss stop being opposites. Both become the same condition, separated only by the patience of the clock. The viewer assumed that some endings are final. The cosmos disagrees, but the disagreement carries a price that no equation can waive. Every black hole is a bomb. Every bomb is a waiting room. And the first waiting rooms built in the opening fraction of the first second are finally releasing the contents. Somewhere, right now, a flash of ancient energy is crossing the void. A telescope catches the signal. Nobody knows what the signal means, not yet. So here is what we know. Quantum gravity predicts a flaw beneath collapse, and every black hole is a bounce frozen in slow motion. But what this really means is that the universe does not allow permanent destruction. Every object we thought was a grave is a storage container on a timer. Every time we think we have figured the cosmos out, the next discovery rewrites the rules from the ground up. These videos are a labor of love. The production takes a lot of late nights, a lot of research papers. If you want to help by hitting that like and subscribe buttons, that would really help me out. I am incredibly grateful for everyone who has supported the channel so far. Your support allows me to keep digging deeper into the strangest corners of the cosmos. But mostly, I want to know what you think. Did I miss anything about Planck stars or the idea that black holes eventually explode? Do you think the bounce is real, or does the whole proposal sound too good to be true? Let me know in the comments. I will catch you in the next one. Let curiosity guide you. Keep learning and know that you are always appreciated.